Okay, hello everyone. Hello Gr12s. Thank you so much for joining me again in lesson two of our lesson. And yesterday I gave you an introduction of our topic, work energy and power, and I tried to remind you of some of the topics or some of the concepts that we have done in our previous classes, like energy and mechanical energy, kinetic energy, and gravitational potential energy. So today we are starting on work done. All right, we are starting today on work done. So we are going to learn how to calculate work done by a specific force. Is that okay? Now, we need to understand how do we calculate work done and how do we substitute different variables in the formula. So the formula that we are going to use for calculating work done, it says work done is equals to a constant force multiplied by displacement multiplied by cos theta. Right. When you look at the formula, you would realize that for us to be able to have work done, there must be a constant force, which is our F, which is acting on an object, and the object must move a certain distance, which is represented by delta x, and then cos theta, theta is going to be the angle between the force and the direction of motion or a direction of displacement. So allow me to write here to label the formula where your W here represent your work done. All right. And your work done, remember we said work done is equals to energy transferred. So your work done is also measured in joules because it's a form of energy that has been transferred or that has been gained or lost. All right. And what is our F according to the formula? This is the force acting on the object. So this is force acting on the object, right? And the force is always measured in what? Our force is always measured in newtons. And then we have got our delta x. This is the displacement, right? How far did the object move? And our displacement is supposed to be in meters. And then we have got theta. Theta is an angle there. What is theta? Theta represents the angle between the constant force. So theta is the angle between the force and the direction of motion or the direction of our displacement. Right. So you will appreciate it. You appreciate our theta better as we do more examples, right? That's when you are going to see how we determine our theta. Right. So this is the formula that we are going to use to calculate work done. And I wish to give you this very important point under NB, which says work done is equals to energy transferred. All right. So what this statement means is whenever we have got work done, energy is transferred, right? So energy can be transferred from the object to the surroundings, or energy can be transferred from the surroundings to the object. Is that okay? So we have got three types of work done, right? We have got three types of work done. We have got what we call positive work, right? And then we have got what we call zero work, all right? And then we have got what we call negative work done, right? So we are going to explore and find out what's the difference between the positive work, zero work, and negative work. But maybe just to preempt a bit, when we have got positive work, it means the object has gained energy, right? It means the object has gained what? Energy. And zero work, it means there is no change there in the energy. And the negative work, it means the object has lost, right? The object has lost energy to the surroundings. So these are some of the things that we are going to be dealing with as we move forward. So for now, let me calculate one example on work done, and I'm going to show you exactly how we use the formula for calculating work done, right? So suppose I've got a scenario here. I've got uh, I've got my object. I'm going to draw the diagram here quickly, right? I've got a block. I've got a block here, and the block is being pulled to the right by a force of, let me say, 100 newtons, and the block moves a distance of, let me say, 15 meters, right? And the first question that we want to attempt, which is item A, remember this is our example one, right? This is our example one. So under example one, this is what we have. We have a block, and the block is being pulled by a force of 100 newtons to the right, and it moves a distance of 15 meters. Remember, if it doesn't move, then there is no work done because your displacement is going to be zero, right? So item A, we are going to be requested to draw a free body diagram. So item A says, draw a free body diagram, right? A free body diagram and show show all the forces acting on the block, right? That is our item A. And item B, it says calculate. We get into calculation now. Calculate the work done by force applied or applied force, right? So these are the two questions that we are going to answer as our example one. Now, we analyze the diagram. We look at it nicely. We have got a block. We are not given the mass, and it's not important at the moment. We are worried about three items or three things here. We are worried about the magnitude of the force which is pulling the object. We are worried about the displacement, how far the object is going to move. We are worried about the theta, which is the angle between the force and the direction of displacement. Right. So let me uh, do the first one, which is the free body diagram. So this is going to be my solution. Right. So our free body diagram, I put a dot, right? That dot represents the block. Then I have to indicate, I must identify all the forces that are acting on the object. So the first force that we can see there, which we cannot dispute, it is the force applied, which is going to the right. So you indicate your force applied there. And then this object, right, it has got mass, so it has got weight. So it is always downward. So this represents my Fg or weight. Now, there's another force that is acting on this particular object, which is a contact force, and that force is known as normal force. Now, what is normal force? Normal force is a force that is exerted by a surface onto the object when the object is in touch with the surface. And normal force is always perpendicular to the surface. and it is a contact force. So it means since the block is in touch with the surface, we've got normal force there. So normal force is perpendicular, so it goes up. So that's going to be my Fn. Now, when we check the normal force, if it's correct or if it's not correct, we use the ruler. We can use the ruler to check if that creates 90 degrees. This is supposed to be 90 degrees, the angle between surface and Fn. It's always perpendicular to the surface. So for now, the question is silent about frictional force. So let's assume friction is not there. So these are the three forces that are acting on the block as it moves through a distance of 15 meters. We've got force applied pulling the object. We have got weight. We have got our normal force. So this is the free body diagram that we can come up with. Then I move on to item number B, which says calculate the work done by force applied. Right. How do I calculate work done by force applied? The formula says work done by force applied is equals to the magnitude of the force applied multiplied by the displacement multiplied by cos theta. That is the formula. So if I was calculating work done by friction, that was supposed to be work done by friction is equals to frictional force by displacement by cos theta, right? So here we are dealing with force applied. So work done by force applied is equals to force applied by displacement by cos theta. So work done by force applied is equals to, what is the magnitude of the force applied? It's 100 newtons, right? Times the displacement. How far did the object move? 15 meters. Times cos. Who is my theta here? What is our theta here? Sorry. So our theta is supposed to be the angle between force and direction of displacement. So where is the force going? To the right. You can see it there. It's horizontal as well. So force is going to the right, and the object is also moving to the right. So it means our theta is 0 degrees, right? So I'm sure cos 0 gives us 1. You can confirm that with your calculator that cos 0, it gives you cos 0 gives you cos 0 gives you 1 there. Confirm that on your calculator. So your work done by force applied is going to be 100 multiplied by 15 multiplied by cos 0. That gives us 1,500. And remember, this is work done. This is supposed to be in joules. And then what do? We underline our answer. So that is the work done by force applied. Right. I'm going to do one more example, which is going to be our example 2 on the work done. So I'm going to draw another diagram that is going to lead us um, through the calculation. All right. Now, suppose now I've got the surface there, and then I've got my block. All right. And this block is being pulled by a force applied of 120 newtons, and the angle theta there is going to be 35 degrees. So the block is being pulled at an angle of 35 degrees, right? And the question is also silent about frictional force, which means at the moment we are not dealing with a frictional force, right? So the first question again, so this is our example. This is our example 2, right? So item A again says, I'm just going to summarize it and say, draw a free body diagram. So you guys, you must know that obviously we must indicate all the forces. That is the principle, unless stated otherwise. So draw a free body diagram, right? Then item number B, calculate work done by applied force. So I want us to deal with the issue of theta for now. That's why I'm only considering work done by force applied, work done by force applied. Then when we understand the concept of theta, then we can start inviting and including other forces like friction and others. Right. So my solution, very quickly here, for item A, draw a free body diagram. Right. So the free body diagram that I'm going to consider, I put a dot, and this dot represents the object that you are dealing with. Now, I identify the number of forces that are acting on that particular block. And remember, in exam, normally the number of marks represent the number of forces. Right. So what are the forces that we have here? We have got our force applied at an angle. So that is my force applied. And then I've got my FG there. Then I've got my FN also. And these are the forces that are acting on the object, right? But as science students, I know when they request you to calculate or to draw the free body diagram, that is exactly what we must reproduce. But allow me to explore a bit, allow me to expand this a bit. We can also have another free body diagram. Yes. In exam, of course, we advise all our learners to draw this first free body diagram where you represent force applied as a vector, as a force, not components. But allow me to draw also another free body diagram where I resolve the force applied into components. We need that other free body diagram for other calculations, right? So I can come up with another free body diagram and I resolve my force applied into components because it is at an angle. So I'm going to have my FG there. I'm going to have my normal force going up, and then I resolve force applied into components, right? So I'm going to have my Fx, which is the horizontal component, and I'm also going to have my Fy, which is my vertical component, right? So the second free body diagram represents exactly the same scenario that we have on the first free body diagram. So those two components, Fx and Fy, they represent our vector, which is force applied there, right? So we need the second free body diagram for calculations, right? But for exam purposes, when you answer in exam, on your answer sheet, we expect you guys to draw the first free body diagram where you represent force applied as a force, which is a vector. Is that fine? B, item number B, which is the calculation, calculate work done by applied force. Now, allow me to divide this board uh, into two sections. So I'm going to calculate work done by applied force using the first free body diagram and calculate work done by applied force using the second free body diagram. Right. So the first one, work done by force applied is equals to the magnitude of force applied by displacement. Oh, I did not indicate displacement on my diagram. It's fine. It's not a problem there. Let's say this object moved for 12 meters. Right, it's fine. We put our 12 meters there. Now, work done by force applied is going to be force applied by displacement by cos theta. Let's substitute. So work done by force applied is equals to magnitude of force applied is 120 times displacement, which is 12 times cos. Now, this one, what is going to be our theta here? Remember, I want to repeat this. Theta is the angle between force and direction of motion. The object is moving horizontally to the right. Force applied is also going to the right, but at an angle of 35 degrees. So my theta is supposed to be 35 degrees. Right. So we need our calculators there. Take your calculator. We need cos 35. So work done by force applied there is equals to 120 times 12 times cos 35. So cos 35 times 12 times 12 um, times 120, 120, then I'm getting 1179.58. Remember, we round off our answers to two decimal places, and this is in jewels, and then you close, you underline your answer. You guys, you can verify that. Maybe human error can kick in, and you realize that my calculator did not give me the correct answer. But just punch cos 35 by 12 by 120. You must be getting your work done there. So that's how we calculate work done, by applied force. But now let me see if I use the second free body diagram where I have resolved my force applied into components, can I still get the same answer? Right. So if I get the same answer, then it means we are all going to declare that this second free body diagram can work when we do our calculations. So we'll consider this first free body diagram as our first option, and then that other one as our second option when it comes to our calculations. Right. So let's move on. How do we calculate work done using the second free body diagram? It's not going to be force applied now. It's going to be work done by Fx, which is the horizontal component, and this is equals to Fx, which is the horizontal component, by displacement by cos theta. Right. So we substitute work done by Fx is equals to, now we need to determine our Fx. Right. How do we calculate Fx? That is very interesting now. Now we need our mathematics here. We need to remember our mathematics very well. Our trig ratios now, they work here. How do we calculate our Fx, which is the horizontal component of our force applied? So you realize that our Fx, quickly I'm going to calculate it here. Our Fx is equals to our force applied by cos theta. Right. So Fx is equals to our force applied is 120 times cos. What is our theta? The angle of the force, which is 35 degrees. So that gives us our Fx. So allow me to substitute with that direct into the formula for work done. Right? So I'm going to put, instead of writing Fx, I'm going to put 120 times cos 35 degrees. So this expression, 120 times cos 35, it represents Fx, which is our horizontal component, times displacement, it moved for 12 meters, times cos. Now, our theta, let us monitor and master our theta here. Theta is the angle between force and the direction of displacement, right? So where is our Fx, the horizontal component, going? It is going to the right horizontally. And where is the object going? To the right horizontally. So it means our theta for cos is going to be 0 degrees. So now we need our calculator. Again, we need to cos 0. We have realized that it gives us a 0. So we need cos 35, yes, times 120. We multiply by 120. I'm just using my calculator here, times 12. And then we get our answer, which is 1179.58. And we underline, like science students, we underline our answer. And our unit is joules. Now, I had closed the first part. Now I open it and check if we are getting the same answer. Now I have to compare the two answers. I realized that I got exactly the same answer that I got using the first free body diagram. So let us make this conclusion together, that if we are given our force at an angle, we can resolve it into components. We can use these components to calculate. Uh, we can use these components to calculate work done by that particular horizontal component, and we get the very same answer like what we get if we use force applied itself. Right. So our calculation is done. We got the same answer. So we are going to declare this one as option 1. So it's up to you now as a learner, you decide. That's option one, and this one we declared to be option two. So it's up to you now. In exam or when you do your classwork or homework, you decide which one to use. Do you want to use option one or you want to use option two? Which one is easier for you? So, friends, before I break, I take a break on this video, which represent our lesson two. There are points that I wish to explain to you. The reason why I'm leaving FN and FG for now is very simple. They do no work on the object because they are perpendicular to the surface, right? So that's why, that is the sole reason why I'm deliberately ignoring them. In our next lesson, I'm going to explain using calculations why we don't consider them and how we get that zero. But for now, I think you can, like science students, you can start to explore and you can see that if we consider perpendicular forces, their theta is going to be 90 degrees. And from your knowledge, your mathematics, you know that cos 90 gives you zero. So all the perpendicular forces, they do not work. So in our next lesson, I'm going to explain that. I'm also going to do two examples on that. And then I'm also going to show you how to calculate net work done in my next lesson, which is going to represent lesson three of our topic, work, energy, and power. Thank you so much for following, and thank you so much for um, everything.